Here we are going to compare the gravitational force on an object at the Moon's surface to an object at the Earth's surface. The mass ratio of the Moon and Earth is 81 to 1. By the way, I should have written these words the other way around. It's the Earth that is 81 times more massive than the Moon. Most people probably know that. The radii ratio of the Moon and Earth is 11 to 3. And most people probably know that the Earth's radius is greater than the Moon's radius. So let m1 be the mass of the Earth, m2 the mass of the Moon. So here's the ratio of the mass of the Earth to the mass of the Moon. m1 divided by m2 is equal to 81 divided by 1, which is 81. So we can write this as m1 equals 81 times m2. The mass of the Earth is 81 times the mass of the Moon. Okay, we get a similar relation for the radii of the Earth and Moon. R1 over R2 equals 11 over 3. So 11 R2 equals 3 times R1. Now, the formula involves the distance between the center of the Earth and the center of the mass, little m. You can see that if the mass is near the surface of the Earth, this distance is very close to the radius. The radius of the Earth is so huge compared to a mass that's a small distance above the surface that we can ignore that small little distance. And similarly for the Moon, if the mass is only a small distance above the surface of the Moon, we can say the distance of the mass to the center of the Moon is equal to the radius of the Moon, r2. So let's call F1 the force on little m due to the Earth, and let's call F2 the force on little m due to the Moon. So we want to compare these two forces, so we can just divide one force by the other to get the ratio. So we divide above and below by g, divide above and below by m. Okay, we're comparing the force on the same mass, of course, little m. Next we are going to plug in for R2. We're going to write R2 in terms of R1, and we will write M2 in terms of M1. Okay, so we're going to get an R1 squared on top here, which will cancel with this one. The denominator shouldn't be squared here actually. So conveniently M1 goes out. Squaring out 3/11, we get 9 over 121, and we multiply above and below by 81 to get 729 over 121. We could write this fraction as a ratio. F1 is to F2 is 729 is to 121. So this is the force on the mass due to the Earth divided by the force on the same mass due to the Moon. 729 divided by 121. So this number works out to be 6.02. So the force of the Earth on the mass is about 6 times the force of the Moon on the same mass. Now we can compare the acceleration due to gravity for objects near the surface of the Earth and the surface of the Moon. To do that, we just use Newton's second law. Okay, so say for the force of the Earth on the mass, that's F1 equals m times A1. Well, we know what A1 is for objects near the surface of the Earth. It's 9.8. It's also known as G. If the resultant force on the same mass near the surface of the Moon is F2, then by Newton's second law, that's given by the mass by the acceleration due to gravity for objects near the surface of the Moon. But we know from the previous part that the force of gravity due to the Moon is about 6 times weaker than the force of gravity due to the Earth. So we divide mg by 6.02. So this quantity here is the acceleration due to gravity near the Moon's surface. So if the force goes down by a factor of 6, the acceleration due to Earth's gravity goes down by a factor of 6. So we just divide 9.8 by 6.02. If you do that, you get 1.63 meters per second squared. Okay, let's look at this question here. At what height above the Earth's surface is the acceleration due to gravity equal to the Moon's? By the acceleration due to gravity at the moon, we mean at the moon's surface. So we saw previously that that acceleration is 1.63 meters per second squared. So how high up do we have to go above the Earth's surface for the acceleration due to gravity to drop down to this value? Okay, so r is the distance between the center of the Earth and the mass, and the force of gravity we know is given by Newton's law of universal gravitation. If this is the resultant force on this mass here, then by Newton's second law the acceleration is given by the resultant force on this object divided by its mass. So that's F equals ma for this mass. So we divide this by little m, and of course the little m's cancel out. And what do we want? We want little a to equal 1.63. So it's only a matter of solving this equation for r. Okay, so to find r, we just interchange r squared with 1.63 and take the square root. I've filled in for capital G and capital M the mass of the Earth. We get 15.7 by 10 to the 6 meters, 15.7 million meters. So for one thing, this distance is a lot greater than the radius of the Earth, as we'd expect. The radius of the Earth is 6.4 million meters, so we have to add on, roughly another 9 million meters. 9 million meters is about 9,000 kilometers. Okay, so we have to go up approximately 9,000 kilometers to get to a point where the acceleration due to gravity is the same as that at the surface of the moon. Now notice in many of these calculations that the mass does not matter. The size of this mass does not matter. The acceleration does not depend on the mass. Because when we use Newton's second law, we are dividing the law of gravitation by that mass, and they always cancel out. So the acceleration due to gravity of an object is independent of its mass. So we could make this mass as small as we like or as big as we like, and the acceleration is always going to be 1.63. Well, for this particular mass. For masses near the surface of the Earth, the acceleration, as we know, is 9.81. The gravitational attraction of the moon on water at the Earth's surface is enough to move the tides. So we are going to get the gravitational attraction of the moon on 1 cubic meter of water at the Earth's surface. Now, 1 meter cubed of water has a mass of 1,000 kilograms. So that's our little m in the formula. Big M is the mass of the moon. It's the mass of the Earth divided by 81 actually. Now, the distance of the surface of the Earth to the center of the moon is about 400,000 kilometers, which is 400 million meters. Calculating this, we get 0.03 newtons. Newton's law of gravitation says that any two spherical objects are attracted to each other with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Okay, let F be the force between these two spherical masses. F is proportional to the product of the masses, so let one mass be called big M and the other mass little m. So what does this mean? Well, it means that if we double any of these two masses, we will double the force. So, if we replace big M with a mass that's twice as big, 2 times big M, then we double the force. Or if we replace little m with a mass that's twice as big, 2 times little m, then we also double the force. Or if we multiply big M by 3, we triple the force. Or if we multiply little m by 3, we triple the force, and so on. Now we are given that F is inversely proportional to the square of the distance between their centers. So the magnitude of the gravitational force is proportional to 1 over the square of the distance between the centers of the two masses. So that distance is little r. So what does this mean? Okay, so this is the mathematical statement of inverse proportionality. Okay, F is proportional not to r squared but proportional to 1 over r squared. So it means that if we replace r with say 2r, if we double the radius, double the distance between the centers of the two spherical masses, what happens to the force? That should be 2. Okay, so I'm replacing r with 2r. I've doubled the distance between the centers of the two masses. Well, what will this work out to? Well, this works out to 1 over 4r squared. So how does 1 over 4r squared compare to 1 over r squared? Well, we can see that the mass has gone down by a factor of 4. I'm sorry, the gravitational force has gone down by a factor of 4. Okay, so doubling the distance between the centers of the masses has the effect of reducing the force by a factor of 4. So the force that we get is only quarter what it was. And we can imagine, say, replacing little r with 3r. Multiply the distance between the centers by 3. Well, we're going to get a 9 here. So the force now will go down by a factor of 9. So the force will only be 1/9 as strong. So that's what is meant by the gravitational force being inversely proportional to the square of the distance between the two masses. So in general, as the distance goes up, the force will go down in this inverse proportional relation. We can combine these two proportionality relations into a single proportionality relation. So we haven't changed anything. If I double big M, I double the force. If I double little m, I double the force. If I double r, the distance between the centers of the masses, the force goes down by a factor of 4. So everything follows if I just combine these two relations together. I haven't violated anything. If one quantity is proportional to another quantity, it means that the first quantity must be a scalar multiple of the second quantity. It must be just a constant multiple of the second quantity. Now the constant of proportionality here has the value 6.67 by 10 to the minus 11. It's denoted by capital G. The units are Newton meter squared over kilogram squared. That makes sense because all of this quantity must have units of newtons because it's a force. Okay, so if we just look at the units by themselves, the units of G are Newton meter squared per kilogram squared. The units of mass are kilograms, but this is so many kilograms, little m is so many kilograms, so we've kilograms times kilograms, that's kilograms squared, and underneath we have a distance squared, that's meters squared. So the meter squared cancel out. The kilograms squared up here cancel out as well. We have kilograms squared underneath the line here and multiplied by kilograms squared from the two masses. So we end up with units of newtons. Okay, that was just more of an aside. Let's look at some examples. Okay, so the force on each mass is the same. So the force on big M is the same as the force on little m. Let's look at the force on big M. It's an attractive force. I mean, big M is attracted towards little m. We could write it like this. It's the vector F, the force on big M due to little m. Okay, following the convention that we saw in previous videos. So really I could have big force on big M due to little m here. What else is it due to? We're dealing with just the gravitational force on big M due to little m. By Newton's third law, there's an equal and opposite force on little m due to big M. So Newton's third law is implicit in Newton's law of gravitation, actually. These two forces are equal in magnitude but opposite in direction. So I'm only showing the magnitudes over here. You can see that the magnitudes are the same. Now we have already seen that the acceleration due to gravity of an object at the surface of the Earth is 9.8 meters per second squared. Now this result actually comes out of Newton's law of gravitation. So let's consider a mass m, I'll denote it by little m, at the surface of the Earth. Now, it might be a certain distance above the surface of the Earth, but that's not going to matter too much as long as this mass is close to the surface of the Earth. As long as the distance of the mass to the surface of the Earth is small compared to the distance of this mass to the center of the Earth. Actually, I probably should show m a little bit closer than what I have it here. Now, we know that the magnitude of the gravitational force on little m is given by this formula here, and it's directed towards the center of the Earth. So this is the force on little m due to big M, where big M is the mass of the Earth. R is the distance between the centers of the masses. Okay, so little m is assumed to be a spherical mass. Well, it won't matter because it's so tiny compared to big M. We're getting the distance of the center of big M to the center of little m. Okay, that's our R. And you can see that for objects near the surface of the Earth, that value is essentially just equal to the radius of the Earth. So as long as the object is reasonably close to the Earth, at least this distance is small compared to the radius of the Earth, which is 6.4 by 10 to the 6 meters, about 6.5 million meters, then we don't have to worry too much about the value for the acceleration due to gravity of little m. So okay, we have an expression for the force of gravity. We need to just fill in for g and the mass of the Earth. The mass of the Earth is 6 by 10 to the 24 kilograms. Okay, so this blue vector here is the direction of the force on little m. What about the acceleration? Well, by Newton's second law, the acceleration is in the same direction as the resultant force. So we are assuming that this is the only force acting on this mass here. Well, it's certainly the only force that's significant. Well, if we leave out electrical forces or magnetic forces, we're going to forget about them. Pretend that this is the only force acting on little mass m. So we just apply Newton's second law. This force is the mass of m, which is little m, times the acceleration of it. Okay, and that's what we're after, and that number is called g in this case. Well, I'll just call it a actually. So how do we get a? Well, if we want to get a, we need to just divide by little m. And you can see that these little m's cancel. So we've applied Newton's law of gravitation and Newton's second law for the resultant force acting on little m. And if you calculate this, you get about 9.8. Okay, and this is given the name g. So as long as we're near the surface of the Earth, our value of g won't change too much from 9.8. You see the distance from here to here, from the center of the Earth to the surface of the Earth, is 6.4 by 10 to the 6. So that's quite a large distance. So if you add on a few hundred meters to the surface, it's not going to make any difference to the calculation. A few hundred meters compared to 6.5 million meters is fairly negligible.